Hello, welcome back. We are continuing with our discussion on trees. Today we look at a special kind of tree called as binary trees. Now, these are special trees where every node has at most two children. Okay? So I'm going to note down this. Every node has at most two children. Okay. So let's look at some examples. What about this? This is a binary tree with one node. And is it a binary tree? Yes, because it has no children, it has zero children. So fine. So remember, every node has at most two children, so it can be zero, one, or two child. Let's look at another example. What about this? This is also a binary tree because both the nodes have, the root node has one child and the other node, the child node has zero children. Again, this is another binary tree, right? Because the root node has two children and other two leaf nodes do not have any child. This is another binary tree. As you could see, all the nodes can be, so the root has two children and this node has two children and this node has zero and this has zero, this has zero. The leaf nodes have zero children, as the name suggests, right? So this is another binary tree. Okay. So all these are binary trees. Fine. Now let's look at a few examples of trees which are not binary trees. What about this? This is not a binary tree. Why? Because the root node has three children. So the root node has three children. That's the reason. Now let's look at another tree. Again, this is also not a binary tree because there's one node which has four children. Okay. So the crucial fact is that every node has to have at most two children. This is the most important fact of a property of a binary tree. Okay, good. Now let's proceed further. Let's see how to implement a binary tree. So as we saw, every node has two children, right? Now we are going to call the children left node and right node. So for example, in this diagram, B is the left child of A and C is the right child of A. This is clear. It's the node which appears on the left is the left child and node which appears on the right is the right child. That's how we are going to represent binary trees in pictorially. Okay. Now, how can I implement this in as a data structure? How will a node look like? Okay. So the node is going to have a node will have like three things, right? Okay. Let me try to. the middle, so this is my pictorial representation. In the middle there will be the value of the node, and on the right will be the pointer to the right child node. That's going to be here. Okay, and on the left, what will it be? It's clear what it should be. It's a pointer to the left child node. Okay. So let's I mean, what will be a typical example be? It's clear, right? If I want to represent the same tree which I have drawn here, how will this look like? This the A is going to be in between, and this is going to point towards a node which has B here, and I'm going to represent, and all the pointers in the child node are going to be null, right? The leaves do not have children, and therefore the pointers will be pointing to null. This is how you can represent a binary tree. The next important thing we are going to, so all the properties of trees which we have considered, we can think in terms of binary tree. For example, what is the height of a binary tree, the depth of a binary tree, right? Now, so then another question which we addressed in trees is the following fact. Maybe in some situations we would want a node to also have the parent information, right? So how do I include the parent information in this node? Okay, you will also have a parent pointer. So let me say here is going to be a parent pointer. It's a pointer to a parent, right? Right. So this is clear. So now if you want to include a parent pointer, there will be 3 pointers in the node and the value. Okay. It's good. Now all the questions which we addressed earlier, you can ask here. How given a node of a binary tree, how do I find the height of the node? Or how do I find the depth of the node? All these things you can answer here. Now, why don't you try to write a recursive algorithm to detect the height of a node? You did it for the case of a general tree, but you can try it for a binary tree. Write a function to get the height of a node. Okay. Now you will see that it's a little more simplified than the original tree function. Okay, why is that so? Because earlier in the tree representation, you had a list of children, and you have to traverse the list of children, and recursively you need to traverse all the child nodes. And in this case, you only have to recurse on 2 nodes, right? Either the left node or the right node. So you can write a function basically which recurses on the left node and also on the right node.